Welcome back everyone. In this lecture I am going to actually get into the bottom of the ground and then show you some examples to like how to construct sets and so on. So, first let us actually begin with some basic logic. So, we need to use quantifiers a lot in mathematics in order to actually, for example, like in order to write mathematics. The language of mathematics is indeed logic. So, one should be comfortable with that. So, for that purpose let us actually go through little bit of logic, and then later what we will do, we will actually see how to construct sets. So, in practice. Okay, so, let us start with some very basic logic. Okay. The most important thing in logic, so as far as practical things are concerned, so we have to be very comfortable in using quantifiers. So, there are two important quantifiers. So, one is denoted as for all. So, this should be read as for all, and then there is another quantifier called there exists. And then there are other quantifiers also that are used. So, other symbols, for example, belongs to, so this is called belongs to, and there exist unique. So, there exists unique. So, these kind of symbols that are used in mathematics lot. So, let us actually start practicing using these symbols. So, let us first actually understand negation, because most of the time in mathematics or in algebra, if you are interested in proving something, so you actually end up writing the negation of that statement, and then that will be useful in order to prove the original statement. So, for example, so let us consider this plain English statement. So, let us say there is a broken chair in this room. Okay. So, there is a broken chair in this room. So, this is given to be plain English statement. What we want to do is we want to actually negate this. So, the negation of this is going to be, so there is no broken chair in this room. So, there is no broken chair in this room. So, now what I want to do, like I want to actually translate this in the language of mathematics. So, the same plain English statement can be actually rewritten as follows using mathematical symbols. So, for example, how one can formulate this? So, we want to first of all kind of make sure that what is the object that we are talking about. So, here we are talking about a broken chair. So, that means we need to consider the collection of chairs that appear in this room. Okay. So, what we can do, we can actually construct this set, let us call it R. So, this set is denoted as the collection of chairs in this room. So, this is the advantage of set. So, set actually kind of adopts everything that are like practical enough to be defined. So, that is why like we will be able to like consider a set that consisting of chairs. So, this is the abstraction level that you should be comfortable in doing mathematics. So, now the statement that says there is a broken chair. So, the being broken is a property of that chair. So, basically if I want to use quantifiers, then what we need to say, So, we need to say there exists a chair C in R such that C is broken. So, this is how we can actually write the same sentence in terms of mathematical language. So, now if you think about it, so if we want to actually negate this, okay, so we are actually pinpointing there exists a chair such that C is broken. So, now what we can do, we can actually want to negate this, then we want to say that there is no broken chair. That means, you give me any chair, I will tell you that it is not broken. So, the negation should be as follows. So, this is the negation. So, for any chair C in R, we have that C is not broken. Okay. So, this is how one writes negation of this mathematical sentence. So, as a simple thumb rule will be like, whenever you see there exists, if you want to negate, you put for all, and similarly whenever you see for all, when you negate, you put there exist. So, let us look at somewhat more complicated sentence. Let us say there is a tree in IISc campus with at least one yellow leaf. Okay. There is a tree in IISc campus that has at least one yellow leaf. Okay. So, if you think about it, the collection here is the underlying set, the set of all trees that are there in this IISc campus, and the property that this tree actually enjoys is that it has a yellow leaf. So, that is the property. So, that means what should be the set? The set should be the set of trees in IISc, the property that it enjoys that. So, one tree that we are able to find in the campus such that it has at least one yellow leaf. So, if you want to write this sentence, then we want to say that there exists a tree T in T such that T has at least one yellow leaf. Okay. So, if I want to say like what will be the negation of this, then we have to say that. So, you show me any tree, so that tree has no yellow leaf. Okay. So, that means for all T in T, we have T has no yellow leaf. Okay. So, this will be the negation of this sentence. So, this is the sentence and this is the negation. Okay. So, similarly like one can write things even using much more complicated mathematical statements. So, for example, you must be knowing about something about the real numbers. The real numbers are actually can be picturized or plotted in the real line. So, now we know that given any real number x in R, so where R is denoted by the set of real numbers. So, then that x actually enjoys what is called order property. So, that means either x is 0 or x is positive or x is negative. So, that is again we can write. So, for any real number x in R, we have either x is positive or x equal to 0 or x is negative. Okay. So, now if you want to actually negate this, so the negation is going to be like, so you can find some real number. So, I am just simply writing the negation, I am not actually trying to say anything about the truth value of that sentence. So, if I negate this, or if you first rewrite this sentence in terms of the mathematical symbol for all x in R, and we have either x positive or x equal to 0 or x is negative. Okay. And the negation of this is going to be, so you can say that there exists x in R. So, that x need not be positive, need not be 0 and need not be less than 0. So, if one of them should be actually happening. So, the best way to actually write this, for example, what we can do, we can actually denote like R plus to make it much more clean way. So, this is just all positive real numbers, and then you have this singleton 0 which is the 0 part, and then union, then you have this negative part which is the minus infinity comma 0. So, now this statement which says that R is indeed equal to this R plus union 0 and union R minus. So, that means what? So, then if you want to say, if you want to negate this, then the best negation will be using these symbols. You can say that there exists x in R such that this x does not belong to this R plus union 0 union R minus. This is simply saying that x is not element. So, x is not positive, x is not 0 and x is not negative. Okay. So, this will be the negation of the statement that you started with here. So, similarly so I would suggest you to actually practice more on negating plain English first, and then later what you can do, you can start rewriting the plain English using mathematical quantifiers and symbols. So, then you can actually again use mathematical quantifiers to negate the original statement that you started with. Again, that practice is very important. So, if you are very comfortable with negating sentence, that will help you to write down proofs in a more clean and proper way. Okay. So, let us do one more example as a practice. So, it's easy to see that it is a true statement that given any real number, if you square it, then it is going to be non-negative. Okay. So, in mathematical quantifiers, you say that as for any x in R, we have x square is greater than or equal to 0, and the negation of this. So, this is going to be, so there exists x in R such that x square is not greater than or equal to 0. Okay. So, we can't say that x square is less than 0 unless we know that order property of R holds, but if I want to just simply negate, then I would negate exactly like this. Okay. Okay. So, this is again very important in order to do some basic mathematics. So, maybe one more example we will do, for example, we can say that a subset of R is bounded, then it is bounded above and then bounded below. Okay. So, maybe let me define a subset A of R is bounded if there exist A and B in R such that A is less than B and A is contained in, let us say, the bracket A B. Okay. So, this is indeed very valid mathematical statement. Okay. So, basically we are defining what is boundedness. Okay. So, now what will be the negation of this? If you think about it, if A is bounded, so that is what given, then you say that the negation of that is A is not bounded. But then the boundedness has this important mathematical definition which says you have an interval bracket A B such that A is contained in bracket A B. So, if you want to negate this, then basically you want to say what should be called not bounded. So, that means, okay, so if I want to say A is not bounded, so then what it means? It means for all A B, given any A B, for all A less than B given to be elements of R. So, we need to say A is not contained in bracket E. Okay. So, if A is contained in bracket A B for some, so for any real numbers A B such that A is not contained in A B, then that would say that A is not bounded, because if there exists A B such that A is contained in bracket A B, then that would imply that A is bounded. So, not bounded should be defined like this. Okay, this should be the negation. So, this is very important, like sometimes we may use a much more complicated way to actually define things, and there will be multiple properties that given set or function will enjoy. So, one should be careful enough to negate things properly, otherwise one may make mistakes in writing proofs and so on. Okay. So, let us actually get to the set theory part. So, now let us actually look at sets. So, we already defined sets using ZF axioms. So, there are bunch of axioms which actually practically tells how to define sets. So, now you can actually, like if you ask me like how to go about constructing sets, and if you think about it, like there are sets that actually already constructed using some meaningful ways. For example, so we will see in this course how to construct what is called natural numbers and then integers and rationals. Okay. So, you may see how to construct real numbers in your real analysis course. So, that we are going to actually not do in this course, but at least the algebraic constructions that we will be doing in this course, natural numbers, integers and rationals. So, these are natural numbers, and these are integers, and these are rational numbers. And the reals will be denoted by R. So, these are real numbers, and then you have something called complex numbers. So, we will see that so we have something called piano axioms. So, that actually kind of used in construction of natural numbers. Indeed, if you assume ZF axioms, then this axiom of infinity that will guarantee that natural numbers exist. So, like once you put it in ZF axiom, then ZF axioms will actually tell you that the existence of natural number. So, that is the way we construct natural numbers. Then from natural numbers to integer, the process of adding inverse of each natural number with respect to addition will give you what is called integers, and then integers will have this multiplication that again coming from natural numbers. Then if you add multiplicity inverse for each non-zero integers, then what you get is rational numbers. So, this is what going on behind the background, but we will actually do it from the scratch and then construct them very neatly, okay, without assuming anything. So, to construct real numbers, we need to have a notion of completion. Okay. There is this metric on R, which is the usual Euclidean metric, and with respect to that, if you complete, then what you get is real numbers. So, that actually uses lots of analysis. So, the construction of real numbers we will not see it in this course, but complex numbers are easy to construct. Once we have real numbers, then complex numbers are nothing but you take elements of the form a plus ib, where ab comes from R, and then this I is a symbol that actually satisfies the property that I square equal to minus 1. And one can make this more rigorously, how to construct complex numbers from real numbers, and that will be done in the later part of the course when you are introduced rings. Okay. So, that means these basic sets will be constructed in this course, and then these complex numbers will be constructed assuming that you have you know what are all the real numbers. Okay. So, these are all some familiar sets which we always work with in mathematics. So, basically the new sets most often you actually define using the previously known sets. The most important thing is sets, actually the language of sets is very adaptive. So, you will be able to actually include anything that you are interested in. Okay. For example, like we said, we can just take the set of chairs that appear in this classroom. So, that is going to be a well defined set, there is no objection. And more generally, we will see later in theory of groups that will be introduced in this course, that there are many interesting ways to construct sets by looking at some properties and so on. Okay. So, we will see what is called the permutations, and one can take set of permutations that will form a set, which are all some abstract things. Still we can collect them and then make sets. Okay. So, that is the most important point. So, the language of sets is very adaptive. So, we can collect everything. So, that is why we will be able to actually use mathematics in many practical purposes. For example, like you must be seen what are the polynomials. Okay. So, if you think about it, so we can also talk about words formed from alphabets. Okay. So, that actually one can take it as set. Okay. So, if you are thinking about polynomial, so polynomial, so let us say we are only talking about one variable polynomial. So, then you actually take a symbol called x, which is called variable. So, then what you do, you actually try to perform, like you try to construct words using this single alphabet x. So, word will be what? So, if you think about the plain English, so words are formed from alphabets. So, if I write for example the, so the means there are 3 alphabets that are used in forming this one word. So, some of the words of course, they have meaning in the actual practical languages that we use, But anyway, anything can be made as word. Okay, there is all possible permutations that you can use. For example, one can also make a word like this, EHT. I am not saying that EHT means something, but EHT is a word that is formed using this 3-letter EHT. Like that, if you think about it, the possible words that you can make using capital X. So, because you have only one alphabet X, so all you can do is you can repeat that X. So, you can take X, you can actually repeat it like XX, XX, X and so on. So, instead of actually writing this as XXXX n number of times, so we, like I said, we use shorthand notation. So, we just simply write it as x power n equal to XXXX. So, this means, so these are all the words that you can make using this letter X, and there is always this empty word. For example, if I do not use any symbol, then I just write some empty space without any symbol, that is still I can consider as word. So, how I actually denote that empty word? For example, I can take the number of x to be just 0. So, I can just take x power 0, which is the empty word. So, if I allow that, then these are all the words that I can make using this letter X. Okay. So, now you can see that I have formed words coming from this alphabet X, and that is a set. So, now what is polynomial? Polynomial is nothing but taking, like if you are talking about polynomials over R, all I am doing is I am taking real linear combination of these words x power n. Okay. So, a typical polynomial will look like a n x power n plus etcetera plus a 1 x plus a naught. Okay. So, then all I do, take the corresponding words and then take the linear combination among them. So, this is my typical polynomial. So, now what I can do, I can also take all possible polynomials like this, okay, and that is going to be my set. So, I can collect all polynomials of this form, a n a naught plus etcetera plus a n x power n, where this a is comes from R and n is coming from, let us say, n, and then I varies from 0 to n. Okay. This is the set of all polynomials that you can make, and usually we denote it by R bracket x. Okay. So, the upshot is like set is very adaptive. So, we can make anything as a set. So, now like for example, like can I do this with more number of letters? Of course, I can do. For example, if I take letters of the form x1 etcetera xn, so then this I can call it as alphabets, and then what I can do, I can just form words among them. So, I can just simply take xi1 etcetera xir, and then I can call this as a word that is formed using this letter x1 etcetera xn. So, like any given language, we have this finitely many letters, okay, and then we make words using those alphabets, okay, or the letters. That is what I am doing. And anything, like I am not saying that anything of this form will have meaning, but anyway, like we can make all possible words, that is permittable. And then what I can do, I can collect all of them, there is no issue. I am not talking about the commutativity between these symbols, okay. I do not care whether xi, xj commute and so on, okay. To begin with, they are just alphabets. So, I do not care about commutativity and all, because most of the time commutativity does not make sense in the actual language. For example, if I take the and if I take het, they are not same. I do not want to treat them as same. Okay. Sometimes when we are considering polynomials, then we allow them to commute, but in general we do not need to we do not need to do this. So, any given word of some length r is going to be some xi1 etc. xir, then r I can vary, and when r is 0 I take it to be empty word, I just call it as 1. Okay. When r is 0, then this xi1 etc. xir, this is called what is called convention. So, okay, you denote it by 1. So, then you vary this I1 etc. IR, and I am allowed to take anything from 1 to n, and you can form a set like this. You collect all possible words and then that actually formed using these alphabets, and that is a set. So, now you see like we have adopted some like more practical way of like even if I say that I have this English language, okay, where I want to consider all possible words formed in English language, that I can consider as a set, because if I start with English alphabets, then all words make sense and that is a set. Now, what I do, I collect those words, okay, which are coming from this collection of, let us say this is my capital X, those words X, sorry W in X, such that W has meaning, okay, in English. So, what I have done, I have taken my alphabets coming from my English language, okay. So, instead of taking this x1 etc. xn, what we do, we just take a, b, c, d and so on. Again, like you also need to use this capital A, B, C, D as well. Whatever alphabets that you are using, use everything. And then if you take these as alphabets, so then let us say the x, let us say this is my alphabets for the English language G, and then XE is the set of words that you make, that set of words that we can make from E. So, then what I can do, I can collect those words that has meaning in English, and this will be subset of XE. So, now we have got some interesting set like that actually kind of practically can be used. Okay. So, I just wanted to give this example, so that like you can see that sets could be anything. Okay. And this is like some more abstract way to construct set, but in practice, like I said, one can start with some standard sets that are known. Then using them, what one can do, one can use some identities, sorry, the functions or some inequalities. So, anything that that are allowed or describing the properties. So, one can use them in order to define the sets. So, for example, so let us actually look at some subsets of R. So, I can just write negative numbers as those x in R such that x is less than 0. So, here what I have done, I have used this property of these real numbers in order to define this set. And similarly, I can also define something like this, x in R such that x into x minus 1 is greater than 0. Okay. This is also something I can actually write. So, I can also write something as like this. Okay. So, this is one way to describe the sets. Of course, as a subset of R, one will be able to identify what they are. For example, if you take this first one, it will be identified with minus infinity comma 0. The same set you can again write it in some other notation, like this is what called interval. So, we can use this in order to write, and you can also like think about it how one can actually identify this set, those x in R such that x into x minus 1 is greater than 0. For example, if x is greater than 1, then that would imply that x minus 1 is greater than 0, and that would imply that x into x minus 1 is greater than 0. So, that means, so this argument tells, so definitely this interval 1 comma infinity is going to be there in this set. But if you think about it, 1 cannot be there. If x equal to 1, then 1 into 1 minus 1 will be 0. Okay. So, that means 1 is not there, but now we can ask like anything else can be there. Okay. So, maybe I will leave it to you to actually find out what will be this set exactly. So, one can also like not necessarily get always non-empty set. For example, if you take x in R such that x square plus 1 equal to 0. Okay. So, whatever the defining property that you are using in order to define the set, it is not necessarily you always get non-empty sets. For example, if you think about it, so for all real numbers we know that x square is greater than or equal to 0. So, for all x in R, so that means x square plus 1 will be greater than or equal to 1. So, that means this set cannot be non-empty. So, this has to be empty set. Okay. So, this could very well happen, and most of the time in mathematics you will be like expected to show some set that you are defining, it is indeed non-empty. So, that becomes actually a hard problem. Okay. So, I will stop here, and we will continue with more examples in the next class, and I will also define functions, and we will see some properties of function in the next class. Thank you. I will stop here.